All right, so let's start. Okay, welcome everyone. And if you are in my previous class, 07 geometry, and you know what I'm going to do for the first 1 minute. First 1 minute is the push up. Okay, so why do I want to do this? For new students, where I just want to use this activity to show us that we need to work hard every day. I work hard every day, so I want everyone else to work hard together with me every day. Okay, so how many push-ups do you want to do? Well, as much as you can. Just try your best. If you can only do one, that's fine. Just do one. If you can do 10, that's good. If you can do 20, that's even better. So everyone, just try. Let's try your best. Okay, find a comfortable place, and we're gonna do a push-up together. All right. So are you ready? Very good. Let's do it. So I'm gonna find a good place. Okay, let's start. Okay. Good. So for this semester, this course, we're going to cover couple of topics. The first one is circle, and then we are going to move to some analytic geometry. Okay. And if we have time, we can go to some other topics, but these are the two main topics. So let's start with circle for today. Today, it's just a kind of a review of some problems in circle. Let's see. So let's see circle. Let's see circle, arc, and a sector. Okay, so let's see. Well, circle, everyone knows that, right? We have a circle here, and the radius of the circle is equal to r, right? So that's our start point. And then I can ask you, well, what's the area of the circle? The area of the circle. I can use A for the circle. This is equal to pi r squared, right? And then I can define the circumference of the circle. The circumference of the circle, which is a c, is equal to 2 pi r. I'm not going to prove that. Actually, in 06 geometry, we actually show that how we can get the circumference of the circle, right? So this is a proved in 06 geometry. Okay, that one. So I'm going to skip that. Okay. Now let's see. Let's talk about the sector. So sector just means if you have a circle here, right? If you have a circle here, and this is the center of the circle, and you have two radians. So this is the O is the center, and A here and B here. So you pick up 2 points from a circle, and then what you get here is that so this part here is called a sector. So this is called a sector, right? The shaded region is called a sector, right? And then we can have the angle here. So this angle, I'm going to use a theta for the angle here. So theta is the angle, is the central angle, right? And this is the R is the radians, okay? And now we can have 2 formulas that we learn. Okay, some people are waiting. Let me move them in. Okay, so we have 2 formulas. The first formula is the area of the circle. So what is the area? Area of the sector. All right, so do you know the formula? Okay, and if you know the formula, just try to understand why we have that formula. So I give everyone 10 seconds. So what's the area of the sector? How can I figure out the area of the sector? The area of the sector is where, first of all, you can have the area of the entire thing, right? The area of the entire thing will be pi r square. So that's a pi r square. But then, since it's not the entire circle, right? The entire circle gives you 360 degrees, right? That's the entire thing. So you need to divide by 360. So that's the area for only 1 degree. But now the central angle has the measure of theta. So I'm going to use theta for that. So that's my formula for the area of the sector, right? In this case here, so let's say theta is in degrees, right? Theta is in degrees, okay? And then we can have the arc length. So let's say I'm going to talk about the arc, the arc, the arc length of the AB, right? So what's the arc length of the AB? Well, the arc length is not the actual distance from A to B, because if we say the actual distance from A to B, that just means it's a direct line segment, but it's not. This is not what we are talking about. So the arc length just means it's a distance around the circle. All right, it's the distance around the circle. So that's called the arc length. The arc length of the AB. So which I'm going to use the AB and then like that, right? At the 2 bars. So that means the arc length. The arc length of that. So first of all, have a 2 pi r. 2 pi r is just the circumference of that circle. And again, I'm going to divide that by 360 and multiply by theta. So these are the 2 formulas for the sector, right? The first one is the arc length. The first one is the area of the sector. The second one is the arc length. Everyone's okay? Right. Okay. So now, next one. I'm going to do where in geometry, where not just geometry, in mathematics, when we measure an angle, okay, when we measure angle, there are 2 different measure system, 2 different ways to measure an angle, Okay, so I'm going to show you. One, the first one is we are all familiar with that. It's a degree measure. So two angle measures. Okay, I'm going to do that. The first one, we know that. First one is a degree measure. And we know this already from 06 geometry, right? That's for sure, right? But today I'm gonna give you another measure. This is called the radian measure. The radian measure. So, so what does that mean? Okay, so one is called the degree measure, and the other one is called the radian measure. Okay, and so here is their connection between them. So let's see. Well, the first one, the degree measure, we all know that like 360, that's the whole revolution, right? The whole circle, it's the angle of the whole circle, 360. Half of that revolution, complete revolution, is 180. That's called the straight angle, right? And then we have the right angle, which is 60-degree, right? And then you can have the 45-degree, 30-degree, etc. It doesn't matter, right? And the unit will be just a 1 degree. So that's a measure from the degree side, right? The degree measure. Okay. But now, what is the radian measure? Well, for the radian measure, I'm going to make the following equation. 360-degree is just a 2 pi radian. Okay, some of you are not familiar with that. So you might say, well, why do I need that? It's, this one is a radian. So you can say something degrees, right? 360 degrees, 180 degrees, right? But I could introduce a different measure. In my measure here, the unit is called the radians measure, right? So 2 pi radians just means it's a complete revolution, right? It's a whole complete circle, right? That angle, I'm gonna call that 2 pi radians. Okay, well, you might wonder, why do we need that? Why do we need that? Well, many of you, for the elementary geometry, usually we don't need that. We usually just say the degree measure, 180 degrees, 260 degrees. Everyone seems to be, very comfortable with that. But I would hear you that when you go to calculus, pre-calculus, and many times we're going to use the radians measure. So that's why I just think that, well, why not we just introduce this at the beginning, right? So in the 08 air geometry, I just decided to introduce the two different measures so that later on, when you study calculus, and it will be very easy for you. So anyway, so 360-degree just means the 2 pi radians. Okay, there's some convenience when we do that later on. Okay, and because of that, so if you divide this one by 2, you will get a pi radians. So pi radians is just 180, and 90 degrees just means the pi over 2 radians, right? And then if I want to do the 1 degree, let's say 1 degree equals how many radians? Can you hear me? 1 degree equals, you can write your answer through chat. So 1 degrees equals how many radians? Pi over 180. Yes, and yes, many of you get that. So that's equal to pi over 180. So that's a conversion. That's a conversion, right? And I can do the other one. How about the 1 radian? 1 radian equals how many degrees? Where you just do the opposite, right? You just do the opposite. So basically, it's 180 divided by pi. That's a degree measure. So I'm going to circle that. So this is a conversion factor, right? How do you convert from one side to the other side? So that's how you can do this. Okay. All right. So let's try a couple of examples. Okay, let's try a couple of examples. All right. So let's see. If I, oh, by the way, 180 divided by pi, this is roughly This is roughly 57.3 degrees. So 1 radian is roughly 57 degrees. Okay. And the other one, 1 degree is roughly 0.1745 radians. Okay, I usually we just write RAD for radians. Okay, so let's see some example for the conversion. Some example. All right, so I'm going to write the following. Pi over 6 radians equals how many degrees? Okay, so give everyone some time. And then I have another one. 2 pi over 9 radians equals how many degrees? Okay, let's give everyone 30 seconds. Let's try that. So how to change from radians to the degree measure? Okay, so let's see. We can do the following. So first, I'm going to have pi over 6 radians. If I want to change that into the degree measure, all I want is that I just want to multiply by a conversion factor. So this is called a conversion factor. Conversion factor just means that where you have either you have 180 degrees over pi, or it's pi over 180, right? So so basically it's pi 180 degree is just equal to pi radians. So this is called the conversion factor. It's called you multiply by conversion factor. All right. A conversion factor is just equal to 1, right? You multiply by 1, you didn't change anything, right? But you change from one measure to the other measure. So what happened? RED, radian, cancel out, pi cancel out. So this is called the conversion factor. Stop sharing. Okay. Still it's not working. Great, very good. So that means I'm going to get the 2 pi radians over 9, and that's equal to pi radian in the bottom, and the top is 180 degrees. Okay, and pi radians cancel with that pi radians, and then 180 divided by 9, that's equal to 20 degrees. So 20 degree times 2. So what do we get here? That's equal to 40 degrees. Okay, so that's the answer. Everybody's okay? Everybody's okay. Let's see. We have very good. So the second one is 40 degree. Good. Okay, let's do the opposite. So here is another question for the opposite. So I want to change a 45 degree to the radians. 45 degree equals how many radians? And then 120 degrees equals how many radians? Okay, give everyone 20 seconds. All right, so this basically says that I'm going to change, I'm going to multiply by another conversion factor. This is on the bottom here, it's 180 degree because I want to cancel out the degree, right? On the numerator should be pi radians. Okay, so this one, 45 and 180. 180 divided by 45, that's equal to 4. So that means it's a pi over 4 radians. That's equal to 45 degrees. Okay, 180. What is 180? Okay, let's see. 180 degrees, I'm going to multiply by pi radians over 180 degrees. Let's see. So that one cancel 60 is a common factor. Right, so 180 divided by 60, that's equal to 2. 120 divided by 60, that's 2. 180 divided by 60, that's equal to 3. So that gave me 2 pi over 3 radians. Everything's okay? You should be able to work on that one. Okay. Anyway, so these are the conversion between the two systems. And furthermore, sometime later on, for the degree measure, you also have, many times you have the 1 degree. I can have the 1 degree is equal to 60. It's called 60 minutes, 60 minutes. And then 1 minute is equal to 60 seconds. It's not a time. It's just happen to call in that way. So if you want to be more precise, right? So 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. So for example, some of the questions it could be well, I don't know. I just make some example like 20 minutes and 35 second 20 degree 35 a minute and maybe 30 seconds. That's equal to how many degrees, right? How do you do that? We'll just convert that one by one. All right, so first of all, I'm going to do this one, right? So 60 seconds is just half a minute. So I can write that to be 20 degree and 35.5 minute. Does it make sense? Right? You change 30 seconds to half minute, right? And how do you do this one? Where this one, you can write that to be 20 plus. And then you want to switch it from minutes to the degree. So you're going to have 35.5 divided by 60. The whole thing is your degree, right? And then you get the answer. I leave the work to you anyway. So that just let you know that. So later on you will have this. Fortunately for geometry, most of the problem it's just a degree. You don't really need a minute or seconds, but I just need you to know this just in case. Sometime in the future you will need that. Okay. Um, anyway. Next the one. Now I'm going to give you the two formulas in terms of, remember that. So for here, for the sector, we have two formulas, right? One is for the area and the other one is for the arc length. But for these two formulas, the theta should be in terms of the degree measure. But what happens if the theta is in terms of the radians measure? What happens? Okay, so I'm going to rewrite the two formulas. So let's see what happens. All right, so revisit the two formulas again. So two formulas again. But in this case here, theta is in terms of the radians measure. Radians measure. All right, so if someone tells you that the theta is in radians measure, how do I figure out the area of the sector? All right, so this is the sector here, and this is the O, A, and B. I need to figure out the area. So I'm going to use A for that. Okay, where again, I do the whole thing. If the whole thing, the circle is pi r squared. Okay, now what can I do here? Where in the previous example, in the previous formula here, we divide by 100, 360 and times theta, because in that case, the measure is in degree measure, right? But now we're in the radians measure. If we are in the radians measure, the whole thing is actually the 2 pi radians. Can you see that? 360 is just the same as 2 pi. Does it make sense? 2 pi radians. And then theta is just here. Does it make sense? The whole the whole revolution represents the 2 pi radians. So the denominator is 2 pi. The numerator is just theta. And then you can see that the pi and the pi can be canceled out. So this is actually 1/2 times theta times the r squared. All right, so that's the one formula. Okay, the other formula. So let's take a look at the arc length. Arc length. So I'm going to have the AB, that's for the arc, and then I'm going to have the absolute value, just mean it's arc length, right? It's arc length of the AB. All right. So again, I use the same idea, or the original one will be the 2 pi r. Okay, but then since it's in the radians measure, the denominator should be just the 2 pi, and the numerator should be just the theta. And amazingly, the 2 pi and 2 pi are canceled out, so that makes things much easier. So it's just a theta times r. So if you can write your angle in terms of the radians measure, the formula is actually easier, right? The arc length is the theta times r. So that's why in calculus, when you do the later on, when you do calculus, the integral, and then you have the formula in a similar way, okay, in an easier way, right? They're actually the same formula, but this can be written in an easy way so that those pi can disappear, okay? So the arc length is theta r, and the area of the sector is 1/2 times theta times r squared. Okay, but I have another way to show you this, which is amazing. Let's see. I'm going to do this. Okay, give me a second. So I'm going to write that in the following way. So it's a 1/2 times theta r times r, right? Because theta r squared, I can write that into a theta r times r. But what is a theta r? Well, theta r is just the same as this one. It's just arc length. So what happens is that is 1/2 times the AB, the arc length, and times the r here. So this is actually a area for the sector. But let me give you a let me uh, let me show you the picture. Well, if you look at that picture, if you look at that picture, did you think of something? 1/2 times the arc length of AB times the R. Here is the R is here. So this is the R here, right? So this is the R is here, and that one is the arc of AB. But this one just similar to the area of the triangle. Can you see that? So that's how I memorize the area of a sector. It's just 1/2 times the height. Can you see that? So the arc length of AB is just like the base of the sector, which is very similar to sorry, I was bumped out, so just came back. Excuse me. All right, so that's what I just talked about. So the formula is similar to the area of a triangle, which is very similar. So similar to the area of a triangle, right? 1/2 times the base times the height. So that's how you memorize that. Okay, so I give everyone 1 minute. Try to memorize the two formulas, and in these two formulas, the the angle is should be in terms of the radians measure. Okay, the angle is in terms of radians measure. The arc length is theta times the rate times the radians r, and the area is 1/2 times the base times the height. Okay, so here's some other definition when we talk about the circle. Okay, where we in when we talk about circle, we need to measure the arc, right? We need to measure the arc, but we can measure the arc length, right? That's the length. But sometimes we are going to measure the arc in a different way. So let's see. Here is another way to measure the arc. Uh, Basically, for let's say, suppose this is like the O, this is the A and B. Again, this is a big circle, right? You got a big circle here. But then you can have some other circle, the small circle like that and small circle like this, right? So you can have, basically those circles, they will have this, they will have the same center, right? So you have the three circles with the same center, right? So one arc is AB, and then the second arc is a CD, and the third arc is a EF, right? And then you can say, well, if I want to talk about the arc lengths, certainly they are different. So if the arc lengths, in terms of the arc lengths, the AB, certainly it's bigger than CD, right? Certainly it's bigger than EF. So if I'm talking about the actual lengths, they are bigger, right? They're different. But on the other hand, if I'm just talking about, you go from, it's just like you're walking from A to B. If you're walking from A to B, I want to see, how much angle you're going to make a change. You're going to make a turn, right? You change your direction from A to B when you walk around the circle. Then basically, the two angles, the angle change from A to B will be exactly the same as the angle change from C to D, as the angle change from E to F. Does that make sense? So if I just don't care about the arc length, I want to see the angle change, right? If I want to walk from A to B, how much was changed for the angle? And if I want to walk from C to D, how much angle was changed? And if I want to walk from E to F, how much angle was changed? They are actually the same. Does it make sense? So in that kind of a direction, I'm gonna do the following. So I'm gonna define a different thing. That's called the measure of arc. Okay, the measure of our arc. Okay, in the measure of the arc, they're actually the same thing. So AB, the measure of the AB is the same as the measure of CD, is the same measure of the EF. I always call that to be the theta. Theta is actually the angle change. Okay, we're going to prove that later on, but at this moment it doesn't matter. Basically, it's just the measure of the arc is just the same as the angle corresponding to that arc. Okay, everyone understand that? So the arc measure is the same as the angle that corresponds to that angle, to that arc. Okay, so this is the angle. This is the angle corresponding to the arc of AB and correspond to the arc of CD and correspond to the arc of EF. So the only difference is that they were in a different circle. But that doesn't matter as long as they correspond to the same central angle, they have the same measure. Okay, the arc have the same measure. So be very careful. One measure is the actual distance. I call that arc length. They are different. The other measure is the arc is the angle change. That's called the measure of the arc. In that sense, the measure of the three arcs are actually the same because they correspond to the same central angle. All right, that's a little bit different. All right, I'm going to give everyone some time. right? Let's think of that. It's just a definition, but that definition is very useful later on when we introduce some theorem in terms of circle. That's very important. So they have the same measure, even if they have different names. All right. So any questions so far? Let's see. If you have questions, just type that in chat. Okay, so in particular, let's see. In particular, let's see. Oh, wait a second. I need to introduce a theorem here. I need to show you something. So let's see. So what's the connection between the two? Well, the connection between the two is the following. We just mentioned that the, the angle, the arc length is equal to theta times r, right? That's a previous formula. Does it make sense? That's the formula introduced earlier. The arc length is equal to the theta times r, right? The arc length is the theta times r. So that's the formula here. So I'm going to use this. But keep that in mind. The theta is just the measure of the arc times the r. All right. So what does that mean here? So this means that the arc length is the measure of the arc times the radius of the circle. Okay. So in particular, in particular, if r is equal to 1, okay, if r is equal to 1, then you got the the arc length of AB is the same as the measure of the AB. They're actually different, right? They have different concept, right? The first one is the actual distance. The second one actually was a kind of angle here. But I write that to be the same. It just means the quantity are the same, right? If R is equal to 1. Okay. So anyway, so these are just the definition. Now let's talk about some example. So let's see some example. Suppose I get the measure of the arc is equal to 72 degrees, right? Again, the measure of the arc is just means the angle. And for the angle, you can have the degree measure, you can have the radians measure. So for this question, let me just give you the degree measure because many people here in this class are more familiar with the degree measure. So most of my problems are in terms of the degree measure. Okay, and later on for all of the problems in the geometry problem, they are all in the degree measure. Okay, the radians measure, I just want you to understand that because later on when you work in calculus, this will become the major measure. Okay, so let's see that. The arc length is equal to 15, and I want to find the radians r. Okay, that should be easy. Give everyone 20 seconds. So let's see, what is this? Right, so this is O, this is A, this is B, 72 degrees, okay? And the length is 15. The length is 15, and I need to find the radians. Okay, well, that should be easy. So first of all, we have the formula for the arc length, right? This is 2 pi r, and I have 72 degrees on the top, 360 degrees in the bottom, right? And that one should be equal to 15, right? So I can set up the equation and solve the equation uh, without much problem. Okay, so let's see. 72 cancel with that. So I can have, let's see, 72, 360 divided by 72. That's 1 over 5. All right, so what's the R here? R is just 15 times 5 and divide by the 2 pi. Okay, so we can get we can get the answer. So that's a 75 divided by 2 pi. So that's equal to the r here, right? That's a radius of the circle. Very good. So excellent. Very good. Everyone get the answer? Okay, next question. Okay, so let's say, suppose, again, I'm going to give you a sector like that, right? So this is O here, and then we have the A, and then we have the B here, right? So suppose I'm going to connect the AB. So AB is equal to 6. Oh, by the way, this one AB just means it's a 9 segment, right? The 9 segment of AB is equal to 6, all right? So let's see, the circumference of the circle. C means the circumference of the circle. So circumference of the circle is 12 pi. All right. I want you to find the following. One is the AB. The arc measure. The arc measure is angle. All right. So there are some. Don't be confused by that. So AB, we have three of them. The first one, AB, means the 9 segment, right? It's the length of the 9 segment. The second one, AB, just means it's a arc measure. The third one means it's an arc length. Okay. All right. So give everyone a minute. Let's try that. Okay. So let's go back to the question. Okay. So if I'm looking for the arc length and the measure of the arc, basically I need to figure out the central angle here, right? Uh, I need to figure out the angle here, right? That's the main thing I need to work on. But how do I figure out the angle here, where you can have you can figure out the r here, because the circumference. So let's see. First of all, the circumference is equal to the 2 pi r, which is equal to 2 pi and 12 pi. So from a circumference, you can figure out the radians. The radians r is equal to 6. That's great. So if r is equal to 6, what happened here? According to our condition, AB, the arc length is equal to 6. So this guy is equal to 6, and this guy is equal to 6. The R is also equal to 6. So we get a 6, 6, 6. This is equilateral triangle. And if it's equilateral triangle, and then I notice that this angle should be 60 degree, right? So I got a 60 degree. So that means triangle ABC is equilateral. Is equilateral. Excuse me. And this implies that the AOB, the measure of the AOB is 60 degree. Now we are almost done. Why we are almost done? So let's see. First of all, what is this one? The arc measure of AB, well, that just corresponds to the measure of the central angle. So that's the angle of the AOB. That's equal to 60 degree. Or if you want it, you want to switch that into pi over 3 radians, same thing. It's the same thing. Okay, so 60 degree, that's a measure of the arc. Okay, that's the first question. Second question, what's the arc length? Where for the arc length of that, where I know that first of all I have the complete cycle, right? The circumference, and then the denominator will be 108, no 360, right? The denominator will be 360. The numerator will be just 60 degrees, right? 360 with 360. So that is actually 1 over 6. That's actually 1 over 6 times the circumference, and the circumference is equal to 12 pi. So 12 pi divided by 6, that's equal to 2 pi. So that's the answer here. All right, so we got the answer. Everyone's okay? Give everyone 1 minute. Any question? So if you're good with that, let's move to the next question. Okay. So we have the sector, okay, OAB. The area of the sector is 12 pi, and the radius is equal to 6. I'm looking for the angle of OAB. All right, give everyone a minute. I'm looking for that one, that angle. All right. All right, so first of all, let's see. I need to figure out the central angle, right? I need to figure out what is the central angle here. That's very important. Okay, so let's see. Where we know the area of the sector. So first of all, the area of the sector is equal to pi r square, and then divide by 360 degree and multiply by theta here, right? So that's the area of the sector. And according to the the condition, we get the 12 pi. Okay, we get 12 pi. So let's just solve that then. So what is this? What is this? Okay, so let's see. Where r is equal to 6. Okay, I'm going to replace r here by 6 here. So r is equal to 6 square. That's much better. Okay, I think pi and pi are canceled out. Let's see, this is 36, right? So theta is equal to 12 times 360 and divide by 36. There cancel out, that's the 3. So 360 divided by 3, that's equal to 120 degrees. Everything's okay? So first of all, you can figure out the central angle, which is 180 degrees. All right, now we need to solve for this triangle here. So what kind of triangle of OAB? OAB is, well, keep that in mind, this is a circle. So OA equals OB. So that means this is isosceles triangle, right? Okay, we are very good. So if it's isosceles triangle, so since we have OA equals OB, then we can get that angle OAB equals angle OBA. And this is in our previous course. I think we proved that sometime earlier, right? I think this is in a 07 geometry, right? We prove by congruent triangles, right? So it proved that. All right. Anyway, so now you're almost done. Why you are almost done? Because let's assume that this is equal to x, this is equal to x, and then by the triangle sum theory, we're supposed to have 180 degrees plus x plus another x, that's equal to 180 degrees, right? The sum of the three angles equals 180 degrees. And now we can get let's say 2x is equal to 60 degrees. Now x is equal to 30 degrees. Very good. Are there any questions? Very good. So what's the idea for this question? We need to go back and first solve for the central angle, right? And after that, we can show that this angle, this triangle is isosceles triangle, and then we can get the two base angles are the same. Solve this equation by using the triangle sum theorem, and x is equal to 30 degrees. That's our answer. Okay. Next question. So first of all, I start with ABCD is a square. Okay, suppose the side length is equal to 5. So that means we get 5 here. All right, we get 5 here, we get 5 here. And now I'm going to draw the two curves. As you can see from here, for the first one is that I can use this as the center. So A is the center, and then I can draw a circle in this way, right? The radius is just a 5, okay? And secondly, I just use a C as a center. I can draw the other circle in this way. Does it make sense, right? And then I'm looking for the shaded region. So that's my question. So find the area of the shaded region. Okay, give everyone a minute. Find the area of the shaded region. All right, so let's do this. So I want to find the area of the shaded region in the middle. Let's think of that. So first of all, I can say that where I want to see the shaded region basically is the following. I can first get a quarter of this circle. So I can get this one, right? So this is A, B, and D. And this one plus the other one, the opposite one, I can get this one here, and then again, it's a sector, right? So this is B, C, and D. But if I add them together, that's too much, right? And now I'm going to subtract the whole square. It looks like a rectangle, but it's actually a square. I'm sorry. Yeah. So it's A, B, C, and D. Does it make sense? So here is what I want to do here. The area of the shaded region is the area of two sectors, right? If you put them together, the middle part was counted twice. The rest of them is counted once. So if you put them together, and then we just subtract the entire square, and that's what I'm looking for. Everybody's okay? Very good. So what can we get here? And the rest of them just try to simplify that. So let's see, what is this? First one, we get the pi r square, right? Divide by 4. Why divide by 4? Because just a quarter of that. Second one, pi r square divided by 4. Same thing. The last one is r square. So what's the r here? R is equal to, what's my answer? I is equal to 5, right? Plug into 5, I think you get it. So let's see. It's just pi over 2, right? Times 25, where I guess I moved the r out. So this one times r square is a 5 square. So that's basically the answer here. Am I correct? Looks like yes, right? Okay. So move the 25 out. So that's the answer here. Okay. Next question. What happened? I have this one here. I have this one. So again, you start with a square here, and then you draw the two sectors, but not in the opposite way, right? The previous question was in the opposite way, but now the two sectors, they are overlapping in a different way here. Now my question is that I want to figure out the area of that shaded region. Okay, two sectors, right? You draw the two sectors in a similar way, but they are not in the opposite way, right? They are close, they are adjacent with each other, right? And so what is the area of this shaded region? So I give everyone a minute. Let's try this. All right, so let's see. Let me try to work on that one. Basically, you are going to suppose this is a intersection point. Let's see. Right. So suppose this is the intersection point of E. Okay. I'm going to connect the DE and AE. Okay. I'm going to connect that. So I, I'm going to show you that the shaded region is actually the following. So first, it is this sector. So you got the A here, D here, and then you have this sector, right? So that kind of sector here. So this one plus the other one here. So you got the A here, and then this is your E, like that. So E is in this way here, and then minus the equilateral triangle. The E is here. So can you take a look? A D, this is A and D. All right, can you take a look why this is correct? So let's see. You know, you have to figure out why this is correct. Does it make sense? Right? Why this is correct? Right. So first you have the end, you have a sectoring this way, right? And then you have a sectoring the other way, right? Something like that, right? And then you subtract the equilateral triangle. Oh, by the way, why this is equilateral triangle? This is just how we construct the picture here, right? Because you use a circle here, the two circles intersect with each other. The two circles have the same radius. So the ADE it's an equilateral triangle, right? Okay, I don't have much time. Let me quickly finish because I have another class afterwards. So just try to finish that. All right. So what is this? This is 60 degrees. This is 60 degrees. So I know this one is actually the pi r square divided by 360 and times 60 degree. The other one, same thing, 60 over 360 pi r square and subtract. This is the equilateral triangle, right? For the equilateral triangle in 0, 7 geometry, and we know that if I have equilateral triangle of 1, 1, 1, the area is square root of 3 over 4. Does it make sense? And so this is a similar triangle, right? All of the equilateral triangle are similar. So I will have 3 root 3 over 4. But seeing the length is equal to 5, it's just r squared. So I'm going to multiply by r squared. Does it make sense? Right? And then just simplify that. So I leave the work to you. Okay. And here's one more problem. We don't have time to finish, but I can just leave the work to you. So let's take a look. Let's take a look. So here's what is this? Okay, so you have the circle here, and in the circle you have two triangles, you know, OAB and OCD. And here we wanted to prove the following. Okay, so the first one is AB equals CD. It just means the actual side, the side, the corresponding side of the triangles, right? So the two sides are equal if and only if. What's the other one? The other one is the AB. It's the arc measure. The arc measure of the AB is the same as the arc measure of the CD. What does that mean? Well, it just means that the arc measure just corresponds to the angle. So there's nothing new here, right? Does that make sense? So this is actually just this guy is just actually the O. Wait a second, AOB, and the other guy is actually the COD. So it's just quite simple, right? If you understand the meaning of that, and you can prove this very easily, right? So if the AB equals CD, if and only if the two central angles are the same. Does that make sense? Okay, I don't have time to write down the proof, and I'm pretty sure you can prove it by yourself. Anyway, so are there any questions? Any question? All right, so if there's no question, I'm gonna stop here and See you next time. Okay. If you have any comments, feel free to email me. Okay. All right. So that's all.
Thank you.
Thank you.
You're very
Bye.
welcome. Bye.
Thank you.
Mhm.